and the central crisis of the Raptor number 3, and indeed, the fundamental barrier to the colonization of Mars is not found in the vacuum of space, but within the microscopic lattice of its own metal walls. As we have established, the full-flow staged combustion cycle is a masterpiece of thermodynamic efficiency. However, in the unforgiving world of aerospace engineering, there is a physical tax for every gain in performance. By achieving near-perfect gas-to-gas mixing and pushing chamber pressures toward 350 bar, SpaceX has created a machine that operates in a thermal regime that should, by all laws of metallurgy, be impossible to sustain. And to appreciate the scale of the melting point problem, one must first confront the raw numbers. The combustion of liquid methane and liquid oxygen in a Raptor number 3 chamber generates a plasma-like environment where temperatures soar to approximately 3,300 degrees Celsius, or nearly 6,000 degrees Fahrenheit. For context, the melting point of the high-strength copper and superalloys used to line the chamber is roughly 1,100 degrees to 1,400 degrees Celsius. And engineers often describe this as the wax paper cup paradox. Imagine trying to build a roaring campfire inside a cup made of thin wax paper. Under normal circumstances, the paper would ignite and vanish in a fraction of a second. The only way to keep the cup from burning is to ensure that the heat from the fire is stripped away from the paper faster than the fire can deliver it. In the Raptor number 3, the fire is a supersonic torrent of gas, and the cup is a precision-engineered thrust chamber. If the cooling system lags by even a fraction of a second, a literal millisecond of thermal latency, the metal will not just weaken, it will undergo a phase change. It will turn to liquid, and the 350 bar of internal pressure will instantly unzip the engine in a catastrophic event known as an engine-rich exhaust event. And the thermal gradient, a war of millimeters. In the world of high-performance computing, a processor might reach 90 degrees Celsius before the system throttles its clock speed to prevent damage. In that scenario, the silicon is only a few dozen degrees away from its operational limit. In the Raptor 3, the metal is operating thousands of degrees below the temperature of the gas it is containing. This creates a thermal gradient so steep it defies intuition. And across a distance of just a few millimeters the thickness of the combustion chamber liner, the temperature must drop from 3,300 degrees Celsius on the hot gas side to under 600 degrees Celsius on the structural side. This is not a gradual slope, it is a thermal cliff. And for the graduate-level reader, this can be understood through the lens of heat flux. Heat flux is the rate of heat energy transfer through a given surface. In a standard gas turbine, like those on a Boeing 787, the heat flux is manageable because the pressures are lower, and the air-to-fuel ratio is designed to keep the flame relatively cool. In the Raptor 3, the heat flux is an order of magnitude higher. We are talking about megawatts of energy passing through every square meter of the chamber wall. And if we look back at our Efficiency Reimagined section, we see that the very factors that make the Raptor 3 elite, the high mass flow and the gas-to-gas mixing, are the primary drivers of this thermal crisis. In older, liquid-injected engines, the droplets of propellant took time to vaporize, creating a slightly cushioned combustion zone. In the Raptor, the combustion is near instantaneous. The energy release is concentrated in a smaller volume, creating a thermal load that is more intense than anything seen in the RS-25 or the Merlin. In the metallurgy of survival, why not simply use a material with a higher melting point? This is the first question often asked by those outside the field. Why not build the engine out of tungsten or tantalum hafnium carbide, which can survive temperatures above 3,500 degrees C? And the answer lies in the structural integrity versus thermal conductivity trade-off. While tungsten has a high melting point, it is incredibly heavy, brittle, and difficult to machine. More importantly, it has poor thermal conductivity compared to copper alloys. In the Raptor number 3, the goal isn't just to stand there and take the heat. The goal is to move the heat through the wall as fast as possible so it can be carried away. And this is why the inner liner of the Raptor number 3 is often composed of specialized copper-based superalloys like SX500. Copper is a thermal highway. It allows the heat from the combustion to bypass the metal atoms and reach the cooling channels on the other side. However, copper is soft. At 350 bar, a pure copper chamber would expand like a balloon and burst. And SpaceX's solution is a bimetallic or composite architecture. They use the copper alloy for its thermal conductivity to manage the 3,000 degrees flame, but they jacket that copper in a high-strength super nickel or stainless steel shell, often 3D printed or vacuum brazed, to provide the structural bones of the engine. The copper handles the fire, the steel handles the pressure, but even this dual material approach has a limit. If the copper reaches its creep temperature, the point where it becomes plastic, and begins to deform under load, the engine's geometry will shift, leading to a loss of efficiency or a total structural failure. In the boundary layer, the invisible shield to survive 3,300 degrees C, the Raptor 3 cannot rely on metallurgy alone. It requires a phenomenon known as boundary layer cooling. And imagine a high-speed river. The water in the center of the river moves the fastest, while the water touching the banks is almost stationary due to friction. In the Raptor number 3 combustion chamber, a similar boundary layer of gas exists against the walls. If the engineers can keep this thin layer of gas significantly cooler than the core of the flame, they can create a buffer zone. And in previous engine generations, this was often done by film cooling, literally spraying a layer of liquid fuel along the walls to act as a liquid heat shield. But the Raptor number 3 is a dry engine. It uses gas-to-gas combustion. Injecting cold gas along the walls is much harder because gases mix so rapidly. If the cool boundary gas mixes too quickly with the hot core gas, the shield vanishes. And this is where the precision of the Raptor number 3 manifolding becomes a life-or-death matter. The injector plate must be tuned with such accuracy that it maintains a cool, relatively speaking, perhaps 1,000 degrees Celsius, sheath of gas along the chamber walls, while the center of the chamber rages at 3,300 degrees Celsius. If the turbulence in the chamber becomes too chaotic, that boundary layer is tripped, and the hot core gas touches the wall. This is known as a hot spot, and in a 350 bar environment, a hot spot can burn through a copper liner in less time than it takes to blink. And the software analogy, thermal throttling and latency. For those coming from a computer science or systems engineering background, the thermal management of the Raptor number 3 is best understood as a real-time control loop problem with zero margin for error. And consider a modern CPU. When you run a heavy workload, the temperature rises. The thermal monitor detects this and sends a signal to the fan controller to increase RPM or to the kernel to throttle the voltage. There is a delay, or latency, between the heat generation and the cooling response. In a PC, that latency is harmless. In the Raptor 3, the workload is the combustion, and the cooling is the flow of cryogenic propellants. And if the pump speed fluctuates by 1% due to a vibration or a sensor error, the mass flow of the coolant, which is the fuel, drops. Because the heat flux is so high, the temperature of the chamber wall will begin to climb at a rate of thousands of degrees per second. The thermal inertia of the system is incredibly low. There is no heatsink large enough to soak up the energy. The system must be in a constant state of perfect equilibrium. And this is why the Raptor 3 flight computer is so critical. It isn't just steering the rocket, it is managing a thermal balancing act. It must ensure that the mass flow of the cooling propellants is perfectly synced with the energy release of the combustion. If the engine is throttled down, the cooling flow is also reduced. The logic must be flawless. You cannot reduce the coolant until you have successfully reduced the fire. And the steady-state illusion. When we watch a Starship launch, the engines look like static, glowing bells of fire. They appear to be in a steady state, but this is a visual illusion. At the microscopic level, the Raptor 3 is in a state of violent, high-frequency negotiation with the laws of thermodynamics. And the melting point problem is exacerbated by the fact that the Raptor 3 is designed for multi-start capability. Every time the engine ignites, the metal undergoes thermal shock. It goes from negative 180 degrees Celsius, the temperature of the liquid oxygen, to its operating temperature in less than a second. This causes the metal to expand. When the engine shuts down, it contracts. And in older engines, this thermal cycling would cause the copper liner to crack, a phenomenon called blanching. Once a liner cracks, the coolant can leak into the combustion chamber, or worse, the hot gas can leak into the cooling channels. The Raptor 3 design must account for this low cycle fatigue. It isn't enough to survive the 3,300 degrees Celsius flame once. The engine must be able to survive the expansion and contraction of that thermal load dozens of times without the metal work hardening and becoming brittle. In the limits of passive resistance, we have now defined the scope of the problem. We have a machine that creates more heat than its materials can withstand, a pressure that wants to shred its structure, and a requirement that it must do this repeatedly without maintenance. And in the history of rocketry, there have been 3 ways to deal with this: ablative cooling, using a material that slowly burns away like the heat shield on a space capsule. This is one and done and useless for a reusable Mars rocket. Heat sink cooling, using a massive chunk of metal to soak up the heat. This is too heavy for a rocket that needs to be efficient. Active cooling, using the propellant itself to carry the heat away. And the Raptor 3 chooses the third path, but it does so with a level of intensity that dwarfs its predecessors. The melting point problem is essentially a hardware limit that SpaceX has chosen to bypass through fluid dynamics. They have accepted that they cannot build a wall that won't melt, so they have decided to turn the propellant itself into a dynamic, flowing shield. And as we move into the mechanics of how this is achieved, it is important to remember that every gram of methane flowing through the Raptor 3 is doing 2 jobs at once. It is a source of energy, or fuel, but before it ever reaches the combustion chamber to be burned, it must serve as the engine's lifeblood. It must crawl through the very walls that are being licked by 3,000 degrees flames, stealing that heat and carrying it back into the heart of the engine. And this leads us to the most elegant and terrifying part of the Raptor's anatomy. To solve the melting point problem, SpaceX does not just use a cooling system. They use a heat recovery system that turns the threat of a meltdown into an advantage for efficiency. and the heat that would otherwise destroy the engine is instead captured and recycled, a process that relies on the regenerative nature of the full-flow cycle. But to understand how a liquid at negative 160 degrees Celsius can shield a wall from a 3,000 degrees fire without boiling away instantly, we must look at the intricate plumbing of the chamber itself. And the melting point problem establishes the stakes of the Raptor's design. It is a machine built to operate in a state of permanent near destruction. The metallurgical limits of the chamber walls represent a hard ceiling on performance that can only be shattered through a radical approach to heat transfer. To maintain the structural integrity of the engine while extracting maximum thrust, SpaceX employs a system where the fuel is the primary defender against its own heat, a mechanism we will explore in Section 5.2, Regenerative Cooling, using cryogenic fuel as a heat shield.